Hey guys, welcome to lesson 2.1.3. We are just continuing on with our transformation adventures. Before we go on to the slightly new stuff, I do want to go over the completing the square to convert from standard form to graphing form, because that is going to be on the quiz this week, and I feel like we could use another go around with that. So here's my equation in standard form, and remember, when you're completing the square you have to use the box. So I'm going to go ahead and make my box right here. Alright, and the setup for completing the square, yikes, okay, I'm going to try that again. The setup for completing the square, remember, is a little bit different than the setup when you're factoring. So when you're doing the box for completing the square, you take your first term and you put it in the top left. Now that is the same first step as factoring, but from here it will be all different. Okay, step 2 is when you're going to take your middle term and you're going to divide it by 2. We're essentially taking this middle term and splitting it in half so that we can put it in these two boxes. We're just dividing it evenly between these two boxes. Alright, once we get to that point, we have to fill out the outside of the box so we can figure out what's in the fourth box. So of course here and here we know x times x equals x squared. And then here we know that x times 2 would give us this 2x, so that tells us to put a 2 here. And when we're completing the square, these two sides should always be the same. Okay, it won't be like that with factoring necessarily, but with completing the square, the whole point of doing this is to get these two to be the same. So if this one's 2, then so is that one. Alright, and then the last number in this box you get from multiplying those two outside numbers, and we have a 2 times 2 here, which will give us 4. I'll pick a different color for that. Alright, so now recall that our goal when we're completing the square is to rewrite the original equation. So our new equation should be equivalent to the original one. But if we only used what we have here and we said, oh, the answer is y equals x plus 2 squared, right? Because that's what this part gives us. We have to realize that that actually only gives us x squared plus 4x. I got the 4x from doing 2x plus 2x plus 4. Okay, this is everything in this box right now. Now the problem is that we need this to match this, and obviously there's an issue, right? We have a plus 4 here, but we want to get a negative 5. So this is where we have to ask ourselves, okay, what can I do to this 4 to turn it into a negative 5? What can I add or subtract? Okay, and then we realize, we're like, okay, well, if I subtracted 9, right, 4 minus 9, oops, okay, never mind, 4 minus 9 would get me the negative 5 that I needed. So I'm going to take that minus 9 and throw it on the end of my equation, and that is going to fix the issue of us having a 4, and it'll give us that negative 5 instead. Alright, and to find the vertex, recall that the vertex is always opposite of h comma k. Okay, our h right now is 2, and our k is negative 9. So our vertex, instead of a regular 2, it's going to have a negative because it's opposite, and the k is still just going to be negative 9. K doesn't change. You take it for what it is. Alright. Down here, I'm not going to do much with this. It's just for you, if you use this as a resource, which I would highly, highly recommend. It's a really great just synopsis or summary of everything that we've talked about so far with transformations. So please use this table, have this near and dear, because it's a good resource to refer to when you forget what each of these letters are for and like all of these details. Please remember that a negative sign in front of your equation flips your parabola. That's not in the table. And also, this is just a note of how to find the vertex. But on to the next page. Alright, so the semi-new stuff for today is to find stretch factors or compression factors, I should have written that, from different forms of equations. Now I know that we're used to finding them in graphing form. That's the easiest way or the most obvious, but you can actually find it pretty quickly from all the other forms as well. So here we know that, okay, this is our A value, and that means that it's our stretch or compression factor. We know this. Because it's a number bigger than 1, it's going to be a stretch, which means it gets skinnier. And if you can't remember that, go back to here and look at this, right? If it's bigger than 1, it's a stretch. If it's less than, like a decimal or fraction, then it's going to be a compression. All right, so that's it for that one. For this one, if you're in standard form, all you got to do is take the number attached to the x squared, okay? That's going to be your stretch or compression factor. Now this time it's a 1/2, and because it's a smaller number than 1, it's a fraction, that means it's going to be a compression. All right, for this one, we can just take that 2. Note that there are no numbers on our x's. If there were, this would be different, but in this case, it's just going to be 2. And because it's a number bigger than 1, it's going to be a stretch. All right, for the next one, we have this graphing form equation. Notice how there's no number at the beginning. What that means is that there's always just an imaginary 1 there, so that's our factor, and it's not a stretch and it's not a compression. Okay, having no number there just means that there is no stretch or compression, so the size of your parabola is just going to be standard. Okay, for this standard form equation, now the last standard form one that we did, there was a number in front of x squared and we just used it. For this one, there is no number, so just like the last example, we are going to imagine there to be a 1. And so again, our stretch or compression factor is 1, and again, there actually isn't a stretch or compression. Please note that I didn't write -1 because that negative is entirely on its own. It has its own effect on the parabola, right? We know that a negative flips your graph. It has absolutely nothing to do with your stretch or compression factor. So please do not write that a stretch or compression factor is a negative number, because that's just not the case. We only want the number, ignore the negative sign if there is one. All right, one more here. Now this is what I was talking about the last time we did a factored form example. There's no number up front, so we can imagine there to be a 1, but these two, right, if we multiplied both of these binomials out, we would get a term from 2x times 3x, and it would be 6x squared. Right, and let me just write all of that. If we did 2x times 3x, we would get 6x squared. And that means that just like in our standard form equation, the number attached to the x squared is our stretch or compression factor. So for us, it would be this 6. And again, because it's a number greater than 1, it would be a stretch. All right, last part here. This one isn't super different from what we've been doing. It's just an extra step, really. So if I give you a graph, you have to be able to write the equation. And so it's important to realize what the original parent function is going to look like. Remember, the parent function of a parabola is the very original one. It's the one before any transformations even took place to it. It's kind of like if you took some Play-Doh out of the container, that's like the original, and then when you start making stuff out of it, now you've transformed it, right? Alright, so here's what your parent function parabola always is going to look like. It's always starting at 0, 0, and this is a standard size. So whatever happens from there, we need to document it. So for instance, let's focus on the vertex. The vertex is the moving point of the parabola. So how did we get from blue to red? That's the question we have to ask ourselves. So we're like, okay, well, obviously the blue moved up 2 units. And then from there, we moved left 3 boxes, right, to get finally to the red. So we're going to write those down. All right, and you might think you're done, but there's one more kind of sneaky yet still obvious piece that we have to include, and that's the fact that this original parabola flipped, right? Now it's opening down, whereas the original was opening up, and that tells us that there was a reflection. Okay, and that means that in our equation, it's going to have a negative sign. So let's go back to these, right? We know that left 3, that's our h. H always represents left and right movement, and it's always the opposite. So if it's left, it's going to be a positive 3. Up 2, k represents up and down movement. So this right here gives us our k. Now k is not opposite, so up just means positive. All right, so now that we have all of these pieces, it's no different than what we've already been doing, right? When I gave you the description of the transformation, you had to write the equation. It's just that now you had to write your own description. So y equals, for the reflection, you got to put that first. Negative sign always comes first. Remember that we aren't actually having a stretch or compression factor here. I've written that here. Whenever I ask you to write the equation of a graph, I'm never going to stretch or compress it. So you can assume it's 1. You can write a 1 there if you want. It's not necessary, so I'm not going to. Okay, the x is always as is. Now we decided that our h is going to be positive, so we're going to do a plus 3. Don't forget to square it. And then our k is 2, and k goes right on the end here, so plus 2. And that is it. We are done writing the equation. If you graphed this equation in your calculator, you would get this red graph. And that's pretty cool. All right, that is all for today. Please let me know if you need any help.